All right. So last time we learned about how to design the insertion sort algorithm, right? And here's what we came up with. So that said, given a list of numbers, we want to design a sorting algorithm that follows the insertion sort idea in order to sort this list. Okay. Uh, we came up with the design here using, say, step-by-step approach, like designing a course algorithm and then refine it before converting that into a pseudocode, right? So you already learned about this. And also last time we showed that this algorithm is always correct. So we use induction in order to prove that the algorithm here is always correct, regardless of how many elements we have for the input or any kind of input we have, right? We'll also show that this algorithm always terminate, okay? And now we will show that, okay, how many steps this algorithm will take for, say, an arbitrary input array. So it's what we want to know, right? And in order to do that, we want to know here, this algorithm will, say, estimatedly spend how many steps in order to finish sorting. So in other words, we are interested in the number of steps. For example, how many multiplication, how many addition, each of such step will take a certain amount of time, and we call it a unit operation of the computer, right? So we want to know how many steps this algorithm will take for an input of size n, where n can be 1, 2, 3, 1 million, 1 billion. So the idea is that we want to have the number of steps this algorithm will take for an input of size n, where n can be any number. And basically, we want to have this number in terms of, say, for example, n squared plus 3n plus 5. That said, we want to know how many steps this algorithm will take based upon the input size n. And if we can do that, then we can expect or, say, predict how long this algorithm will take by plotting the graph here. So for this direction, we have the size of the input. And this direction, we have the time, running time, okay? So if it's n squared plus 3n plus 5, then it will go like this. So we can expect that when n goes, then the time needed for running the algorithm will also go like this, right? If we have another algorithm, in that we have Tn is Tn cubed plus 2n squared, for example. Then when we plot this function, it will go like this. So at any time, when we look at the certain number of input, we know that this algorithm, the cubic one, will take longer time than the square one, the quadratic one, right? So that said, the idea is that we want to know how many steps the algorithm here will take in terms of a function in n, where n is the size of the input, right? And here we want to see when n go to infinity, what will happen. And that is the main idea of how we can predict the efficiency or the performance of an algorithm. So basically, we want to know how many steps this algorithm, we call it timing of the algorithm for the input of psi n. Okay? How can we come up with this? Is what we will try to do. Okay? So we will count how many steps each of these statements will take. So last time we already have here, this for statement, last time we say that for the input of psi n, this for statement will take n step, right? So for here, j from 2 to the n is n minus 1 time the algorithm will go into the loop, plus the last time when it come up here, when j is n, and then increase it by 1, and n plus 1 is bigger than n, then it's finished, right? So that's why we have here n. For this statement, we already know that is n minus 1, okay? Because it comes into this inner loop n minus 1 time for j from 2 to the n, right? So same thing here, n minus 1, same thing here, n minus 1. So now, last time I asked you to see, check by yourself at home to see how many steps we have for this statement. How many steps we have for this statement? How many steps we have for this? Okay? Did you do it? Did someone do it? All right, kind of. Okay, so let's go through the steps for seeing how many steps this statement line will take, right? For the input of psi n. All right. Okay, so before we answer that question, let me remind you of how the algorithm works, right? So starting with here at the beginning, we have j is 2, right? So for this situation, we know that we have to insert this one in. So how many steps or how many times the y condition here can be true? It can be here, we push this one, right? And second situation is that this one is already smaller, so we don't push it, right? So that said, the number of moving the elements in the sorted path depends on the actual input. So we cannot say that this one will take n time, n minus 1 time, anything like that, because it depends on actually what value we have for the input, right? So generally speaking, when we talk at j is k here, right? So we have to insert a k into the list that is sorted before. Then we have many different situations. So here the value can be pushed or moved to the right 1 time, 2 times, 3 times, or k minus 1 time, depends on the values we have, right? So that said, if we say that here for a value of j starting with 2. T2 here is the number of elements we have to move to the right. T2 here can have 0 or 1, right? Meaning A1 just stay, doesn't have to move. And then it has to move 1, right? Same thing, T3 can have is the number of values when we insert a 3. It can be 0, 1, or 2, right? Similarly, for Tk and then for Tn, it can be 0, 2, n minus 1, okay? 0, 2k minus 1. So, that's it. The values in that the while loop here can be true is for j is 2, can be 0 or 1, T3 can be 0, 1, or 2, right? So that's it. Here, inside the loop, the condition is true. How many times we have this? It will be T2 plus T3 plus Tn, right? And now, same thing here, T2 plus T3 plus Tn. Same thing here, T2 plus T3 plus Tn. Okay, how many times this one will be executed? Will be the number of values we have to move when j is 2, and we call it T2. It can be 0 or 1, right? So you can see that we cannot know what is value of T2, but at least we know what is the minimum value of T2, what is the minimum number of values we have to move? 0, 0, 0, 0. What is the maximum number? 1, 2, n minus 1, right? So we know that what is the minimum value, what is maximum value? Mean, max, and average. Those are the values we can know, right? So the mean here, you have 0, max is 1. What is the average? The mean value plus the max value divided by number of cases, right, is 1/2, right? Here, 0, 2, okay? So we have 0, 1, 2, right? So 3 cases, and we take the mean plus the max divided by the number of cases, right? So etc. Okay? Do it by yourself. So you know how we have the mean and the max value. Okay? So that's it. Here we have T2 plus T3 plus Tn, etc. Right? And now, what is the number of steps for this statement? Remember that the while loop will take the number of times we have the condition here are true, right? So, this one we have in one, so we should remove this one. Okay. This one is a condition, not a statement, right? Okay, so we have only this one and this one. Okay, so the number of the while loop statement will be how many times the conditions are true, so we can enter the loop, right? And then one more time when we come up here, to check that the condition is not true, right? So that said, the number of steps for this while loop will be t2 plus 1 plus t3 plus 1 and then tn plus 1, right? Okay, so that said, the number of steps this statement, the while loop here will be executed is here. Okay, this statement is here, this statement is here, right? So totally, how many steps this statement, this algorithm will take? We simply add them up, right? Simply add them up. Then what we have? N plus n minus 1 plus n minus 1 plus n minus 1, right? So we have n plus n minus 1 plus n minus 1 plus this one and this one, right? So this one we can combine 2 times of this. And actually this one we have 3 times of T2 plus T3 plus Tn, right? Plus, okay? So here we have 1 plus 1 plus 1 plus 1. How many times? N minus 1 time, right? So that is n minus 1 plus n minus 1 from here. It's 2 times n minus 1, right? But let me have n minus 1. Okay, so we can simplify this. Here you have n minus 1 4 times, okay, plus n. So that's it. We have 1, 2, 3, 4, 5. 5n plus 3 times this. Okay, plus what? Actually minus, right? Minus 1, 2, 3, 4. Okay, so here is the total number of steps this algorithm will take for an arbitrary size of n. In that, T2 is the number of steps we have to move at the second position, right? How many steps? T3 is how many values we have to move to the right. Okay, same thing for Tn. All right, so in total, here is what we have. Okay? All right. It's the first step. Counting the number of steps for each of the statement line. And now we can come up with, okay, what is the best case situation and what is the worst case situation of this algorithm. Okay, now let's talk about the best case first. Last time when I asked this question, someone already answered that, right? Very good. So the best case situation is that if you have the list here is already sorted, right? So that said, you have A1 is lesser than A2, less or equal A2, lesser than AN, etc. So that said, at every value of the J, okay, we have 0 moving, right? So that said, at this point, because A2 is already bigger, so A1 will not be moved to the right when we insert A2, right? So similarly, the number of steps for the third position is 0, etc. Right? So the best case means that when does the algorithm work fastest, or the smallest number of steps, the smallest number here, we see that they're all 0, right? So that said, the best case situation is that when all of these ones are 0, then what is the number of steps this algorithm will take? Best case, let me write here, and hopefully that I still have enough space. Okay, best case means that when all of the values here has the smallest number, so meaning that they are all 0, so Tn will be phi n, right, minus 4. But when n is big, 4 here doesn't make much sense, right? And same thing, we don't want to have a constant here because phi n or 6n will be very similar when n goes to infinity. And that's why we call this one is big O n, or sometimes theta n actually. Yeah? So the best case is big O n, right? So usually we talk about big O, okay? Or I mean the capital O. So this one is the best case. All right, very good. So now the second question is about what is the worst case situation? Okay, what is the worst case situation? The worst case situation is the case that we normally want to see, meaning we want to see, okay, when does the algorithm work slowest? Okay, so how do I know when this algorithm works slowest or consume the most running time? That is when I have the maximum values, right? The maximum values, meaning the algorithm will have, so for example, here at this point, A1 we have to move to the right in order to insert A2, right? And here same thing, okay, we have to move K minus 1 time before we insert this one here, right? Okay, so that said, the worst case will be here, T2 is what? 1, T3 is 2 to n minus 1, right? Okay, so that is what we have here. That is the worst case situation. Okay, so for a list of numbers, what would be the condition for having the worst case? So give me an example for the list of numbers in that the time for inserting an element take the biggest value. So for example, in this case, we have 1, 2 to n minus 1. Okay, very good. So you already saw that, okay? So it's in the reverse order, or Brian Jacobs have concrete values, okay? They both work, all right? So in that situation, the biggest value for moving or for inserting an element will be here. So we simply plug the values here inside this formula, right? So here we have phi n plus 3 times 1 plus 2 plus n minus 1 minus 4. Okay, so that is the values here. Now we have to simplify this one a little bit. Because as I mentioned before, when we analyze the performance, we want to have a function in terms of n, but that is, say, concise, right? So that is meaning that is short enough. We just pay attention to the biggest term. So that's why we want to simplify this. Okay? How do we simplify this? We just have to find out what is this sum. In other words, here, for analyzing the performance of an algorithm, we have to deal with the summation a lot. And in fact, you already learned the summation, for example, geometric series or the Gaussian series in concrete math, right? So let me remind you a little bit about that. So here we have this sum. What is the value of this sum? If you still remember. We will practice a little bit, okay? Let me remove this one so we have space to write. So when you learn about the summation, and you have, for example, 1 plus 2 plus 3 plus n, what is it? Okay, so in fact, when we write this one in terms of the summation is the sigma of I for I from, say, 1 to n, right? So sometimes you also have it from 0, that is 5, okay? So here we have sum from 1, okay? 1 or 0, we can deal with them both. In fact, here in this situation, if you add 0, the sum will not change, right? Because 0 plus something is still something. So what is this sum? Now, when you learn about the summation here, like in discrete math, right? Many students did not pay attention to the fact that the sum here will help us to speed up the algorithm. For example, ask you to write a program that will take into account the function called sum, right? Okay, for example, I put it my sum. I want you to write a program that will take into account a value n and return the sum from 1 to n. Okay, so that is what I want you to do. Okay, how can you do that? You can design a very simple algorithm, right? For example, you have a variable called sum and assigned with 0, right? And then you have the for loop, okay? For I from 1 to n, you just accumulate the value to the sum, right? So it's very simple. For I from 1 to n, okay? You have sum is a sign with sum plus I. That's it. And then you return sum, right? So return sum. So this program is very simple and it does the job. But how many steps this function will take? Again, you can follow what I did here and count it for yourself. Okay? Follow this step for counting the number of operation. Then you will see that this function will take big O n steps, right? And you will see that this one takes big O n steps. Okay? So big O n step means that when n is going into infinity, the number of steps will also go to infinity, right? And the algorithm here is not a good one. Nobody wants to use this because taking the sum using big O n steps is too much, okay? It works very slow. So that's why we don't want to use the idea here by accumulating. All right? All right. So instead of writing the function like this, I will write my function like this. Okay? I want to have a function that returns the sum from 1 to n, right? Okay, so I will simply write it like this. Return, okay, n plus 1 times n divided by 2. Okay, now this value is the same as when you add 1 to 2 to n. But what is the complexity or the performance of this algorithm? It's no longer big O n. It will take how many steps? One addition, one multiplication, and one division. 3 steps, right? So big O3, or when it's a constant, we simply write big O1 because 3 or 1 are similar when n is big, okay? So that's it. You can see that instead of adding n times, I just have one step, okay? More precisely, one multiplication, one addition, and one division, okay? So that's why in computer science, when you learn about the sum, we pay more attention to how to use it to speed up the design of the algorithm, okay? So that is the idea of learning the sum. And also the sum here will help us to analyze the performance of many algorithms, because many algorithms, when we count the number of steps, we come up with something like this, okay? All right. Now, what is the sum here? And as I just wrote down in the my sum function, this one will be, right, n times n plus 1 divided by 2. Okay. How do I know that? How do I know that is correct? How do I know that this one is correct? Again, we can use induction, right? So that is what we use in order to prove that this algorithm is always correct. Okay? We use induction. Okay. Now, I want to ask you to do it, to prove this one using induction by yourself as an exercise. Okay. So just follow whatever I did for this algorithm. So basically, what is the base case? What is the induction assumption? And what is the induction proof? Okay? So base case is easy. So if n is 1, it's true, right? Because n is 1, you plug it here, you have 1 times 2 divided by 2 is 1. So the sum from 1 to 1, meaning we have n is 1, is true, because this formula will give you 1 as well, right? Okay, so do the induction by yourself as an exercise at home after the class today. All right, now once we know this, we want to use this formula for our purpose, right? So what is it? Here you have from 1 to n minus 1, right? So the sum here, 1, 2 to n minus 1 will be n minus, just substitute n minus 1 to n. You have n minus 1 times n minus 1 plus 1 is n divided by 2, right? So this sum will be here, all right? So when we analyze the complexity of an algorithm, most of the time we don't have the exact formula like this. We have something a little bit different like this, okay? Or sometimes we have it like this. Instead of coming from 1, you have 2 plus 3 plus n. What is it? So when we analyze the performance of an algorithm, we may come up with something like this. And then we have to be able to know what is this sum. It's not exactly with the form you learn in discrete math. But we can calculate this based upon the normal value here. What is it? Can someone write down the result for me? This sum is exactly this, right? Minus 1. So the result here will be the result here minus 1, right? Okay, very simple. So it will be n times n plus 1 divided by 2 minus 1. Okay, that's it. So that's it. Most of the time, we don't have exactly the formula, but we can work out by changing the formula a little bit. All right, so now we will try to use this formula to plug it in here, right? So what is the worst case situation for this insertion sort? Here you have phi n plus 3 times this. Okay, 3 times this, we already have it here. N minus 1 times n divided by 2 minus 4. Okay, so this one is the worst case. All right. But now we need to do a little bit more. Okay. So this one, you have what? 3/2 of n squared minus n. Just multiply the n in, right? So this one will be 5n plus 3/2 n squared, right? Minus 3/2 n minus 4, right? Now, when we have here the Tn is this. So when we have a formula like this, and we know that when n is big, meaning that when n goes to infinity, n squared will dominate the value of n or the value of minus 4, right? So that's why we say that this one is big O n squared. And that's it, the complexity of performance of the insertion sort for the worst case. Okay? So the worst case for insertion sort is big O n squared. All right. The best case, we rarely use it because, as you see, the best case is that the algorithm is already, the input sequence is already sorted. So the algorithm will do nothing, right? And then the worst case means that the list of input values is sorted, but in the reverse order. But this rarely happens in the real life, right? So that's why we want to say, look at the average case. Average case means that the insertion sort, when we run it on an arbitrary list of input numbers. So what would be the average case? So in practice, the average case is the, very precise number we want. But most of the time, the average situation or the average complexity is hard to find. And in that situation, we want to do the worst case. Okay? The worst case means the max value. Okay? It's much more useful than the best case or the minimum number of steps. Okay, now how can we have the average case for this algorithm? Now going back to this, what is the average case? We just have to know what is the average case of T2, T3 to Tn, right? Okay, so let me remove this one for the average case. Okay. The average case, what is the average number of steps that we need in order to, say, insert A2, insert A3, insert A4, etc. Okay, so looking at this, and let me write down the value of the input again, so we can see what is the average case. Okay, so again, we have the input sequence has A1, A2, A3 to AN, right? So what is the average case when we insert A2 into the sorted path? Same thing for A3 and then same thing for AN. Okay, so Tn, here we have T2. And the average case, here you have 0 and 1, right? 0 move, 1 move. What is the average? Average, as we know, is just simply take the sum and divide to the number of cases. So here we have the sum from 0, Now the sum from 0 or from the 1 are the same, right? Because 0 does not add anything into the sum, but here 0 will be counted as one case of the total number of cases. So that's why here we have the average is 1/2, right? The average here is what? 1 plus 2 is 3 divided by 3 is 1, right? Okay. Same thing for tk to tn. So what is the number of, what is the average value here for tk or any value? So here we have the sum from 0 to k minus 1, right? We have it, k minus 1 times k divided by 2, right? K minus 1 times k divided by 2, and all of them divided by k. Here's the sum, and then the number of cases is 0 to k minus 1, that is k, right? Now we can cancel k here and k here. So in general, the value we have here is k minus 1 divided by 2, right? K minus 1 is roughly the same as k. So that's why here we have this. Okay? This sum will become the average case phi n plus 3 times the sum here of T2, T3, etc. The sum of j divided by 2 for j from 2 to the n minus 4. So here is the average number of steps that the insertion sort would need for an arbitrary input sequence of n values. Okay, so here is the average case. How can we come up with this? Because we try some value, and then for an arbitrary k, we know that here's the sum. Cancel k, here we have k minus 1 divided by 2, right? K minus 1 is roughly k for simplifying the summation. Okay, so that is, we want to simplify the sum. If we don't simplify, the calculation will be much more complicated. It's not necessarily complicated. That's why we want to simplify as much as we can. Okay? Now, what is this value? Can someone tell me? I'll give you 2 minutes, okay? So what is the Tn here in terms of big O of what? We know the formula. We have a sum, and I want you to write down the sum, simplify that, and give me the result. And again, the sum here is not exactly the same as the sum you learn in discrete math, but we know how to deal with that, right? Like I did in the previous 2 examples. Okay, 2 minutes and give me the result. Okay, anyone? So you know the sum of j, right? When j from 2 to the n is what we did before, but here's j half. How can we do that? We just bring the 1/2 out. And inside we have the j, right? So just take the 1/2 out because 1/2 is a constant. We multiply with, 1/2 multiply with j, say n minus 1 time. We can take that common factor out and is here and remove this, right? It's the same. And now we know how to do the sum here, right? So that said, this one is n square as well. So that's why we have the insertion sort. The average case for insertion sort is also n square. And we know that the worst case is also n square, right? For the maximum number of steps, it's also n square. So in general, insertion sort take n square step. And that said, we will try to analyze one more algorithm that is the merge sort. And you will see that merge sort is much faster than insertion sort. Okay? We also analyze the heap sort and quick sort lately, but all of them are better than insertion sort because here we have n squared. All right. So that is the complexity or the performance of the insertion sort. Okay, now we have the next topic here. Okay, so here is one hands-on exercise for you. Yeah. So here is what I share with you on the screen. All right. So how to multiply two integers? You know that if we have two big integers, then we cannot multiply them directly because the computer has only the hardware for multiplying 8 bytes or 64 bits number, right? So if we have a big integer or two big integers, then we need to find a way to multiply them together. So that said, we have two different ways. One is the simple method that will take here. The number of multiplication will be Tn is the same as, Tn is 4 times t and half, because for the first number, x, we break it into two parts. X has, say, more than twice the number of 64 bits for the computer, so x will have to be broken into two parts. Same thing for the y, and we multiply them using 4 small multiplication. And that's why we have the running time is 4 times t and half plus 100n, right? Or basically theta n, right? So here is one thing we have, and then the other thing we have is what we call the Karachuba multiplication. It's much more efficient. That takes only 3 multiplication of the small values. Okay, so that's why we have the formula here. Tn is 3 times t and half plus 100n. Okay. So look at these two examples about how to multiply two big integers to have some ideas about why we have to design an algorithm that works best or fastest. Okay? So now the next thing we will do is learning one more sorting algorithm is what we call the merge sort. Okay, so let me show you one example, and then we will try to design a merge sort and analyze it to see how we can come up with the complexity of the merge sort. Okay, at the meantime, while I'm cleaning the board, remind yourself a little bit about merge sort to see if you still remember that. Okay, so let me have one example, a small example here. Okay, so we have a sequence of numbers like this. So let me go back to this one and then stop presenting. Okay, so how does the merge sort work on this situation? When we have the merge sort, what we will do is that we break the list into two parts, right? Search the left, search the right. I mean, sort the left, sort the right, and merge the result, right? So how do I sort the left? I apply the merge sort again to the left half, right? By breaking it again, okay? And then sort the left, sort the right, merge the result, right? So that said, I keep breaking until the list has one element and it's sorted, right? So assume that after I apply the merge sort recursively, I have for the left here two, I mean 1, 2, 4, 8, and here I have 3, 5, 7, 9. Okay, so I have merge sort the left, sort the right, and merge them. Okay. How can I merge? How can I merge? Basically, I will use two pointers, right? Point at the beginning index of the left and the right subhalf. Okay, so I have I and J here. Starting from the first element, meaning that at the beginning is 1, right? Yeah. And I compare. This one is smaller, I will write it down. And at the same time, advance the I. Okay? So I will be here now, meaning I is 2, right? So that's it. we have it here, I is 2. Compare is still smaller here on the left. I write it 2, right? Advance. Whenever I write a value down, I will advance the pointer. Now 3 is smaller, so I write down 3, advance the J, right? Now 4 is smaller, so I will write 4, advance this, right? 5 is smaller, so I write 5, advance. So I have 7, advance. Now I have 8, right? Advance, it will go beyond the size here. So now I know that I have to copy everything left from this, the right half here down. So that's it. It's what I have, right? So I have 2 pointers and then compare, write down, advance, right, etc. So that is the idea of the instruction sort. The merge sort, okay? So let's see how we can design the merge sort. Okay, so as I share with you on the screen, right? We recursively sort the left, recursively sort the right half, and then merge them. So now, how can I count the number of steps here for this algorithm? Okay. I want to know what is Tn for this merge sort. It looks like here I cannot actually count, right? Because this algorithm is a recursive algorithm. So I don't know how many steps does it take for step number 2, for example. Recursively sort the left, recursively sort the right. But I know for sure that the total number of steps needed for this merge sort, if I write it Tn, it will be the cost for sorting the left half plus the cost for sorting the right half plus the cost for merging, right? That's the cost for merging. What is the cost for merging? I write it n here, but let's see. How can we come up with n for merging? Okay, so I explained to you the merge sort, and in that I have the algorithm for merging the 2 sublists, right? Yeah. Follow the steps I did in the class before and design the algorithm for merging. Okay? Don't search the internet, don't try to say look up anywhere, but just try to do it by yourself so you know how to design an algorithm for merging the 2 sorted lists. Okay? The 2 small lists here are sorted. So try to design it by yourself to see how you can come up with an algorithm. Actually, follow the algorithm I explained to you, right? And analyze it to see why I came up with n. Okay? So now, let me stop presenting here. Okay, so that's it. For the merge sort, we have the total number of steps for sorting a list of n elements will be the total number of steps in that we recursively sort the left half, recursively sort the right half, right? Here we have the original list has n, the left half has n half. So if we apply the merge sort recursively, it means that we break the left subhalf into two halves again, right? And then continue that. It will take exactly t and half. And then merge sorts of the right half and half, t and half again. And the cost for merging the results of the left and the result of the right is n. Okay? So, okay, we come up with the total number of steps here, but it's different with what we had when we analyze the complexity or the performance of the insertion sort, right? Okay, the main difference is that insertion sort is not a recursive function. That's why we can come in and analyze the number of steps the algorithm has, right? Here we have a recursive algorithm. And when we have a recursive algorithm, analyzing the performance of a recursive algorithm involved in the formula like this is what we call recurrence. Okay? Now, we want to solve this recurrence by finding what is Tn, in that we have a function of n without the t again. So for example, in this case, I solve this recurrence and I have the solution is n log 2 of n. So here is what I call the solution for this recurrence. Okay? And now we have to learn the next approach for analyzing the performance or complexity of an algorithm, in that the recursive calls are involved. Okay, so you see, we have two different approaches, one for the top-down algorithm and one for the recursive algorithm like the merge sort. All right, now we want to solve this recurrence so we can have a function without a recurrence again. Okay? Meaning that the right hand side is a function in n without having the n in the formula. So how can we do that? So here, actually, the steps here you will learn will be used for solving the third question in the exercise number 1. Okay? Exercise number 1 I posted yesterday, actually last night, has 3 questions. The first 2 questions you can start working from yesterday actually. And the third question, and you can do that after you learn this method. Okay. So, looks like we are running out of time. So I will try to give you a rough idea first, and then next Tuesday we will go into the details of how to solve the recurrence function using first back substitution and then what we call recurrence tree. Okay, so the idea is as follows. We still have some more minutes. Let's give you some big idea. Okay, okay, we want to know what is Tn. Okay, Tn is 2 times t and half plus n. So I will replace Tn here by here I call the extra cost. This one is the recursive call, right? So I will start with n, and then I have t and half and t and half. Okay, this one is what we call recurrence tree, meaning we want to build a tree to show us what would be the total number of steps. Now, we come up with this one. Now we will try to replace this node, the left node, t and half. What is t and half? Just replace n half with this. Okay? Replace n half to n. So here you have t and half will be replaced by here n half, the extra cost. Plus with the left and the right is t and half divided by 2, right? Replace n by n half, then you have n half divided by 2, or n half n divided by 2 square, right? Here tn 2 square. All right, so that's it. Now we know n half, and then coming further, do the same thing for the node here, and if you can, do it at home by replacing this with the extra cost and the subtree for this at home. So on Tuesday, we can continue this process and adding all of the value together, then you would have what is the total cost for this merge sort. Okay? All right. Any question? Try your assignment or exercise number 1 as soon as possible. Then next week, if you have any question, you can ask me. Of course, I will not give you the solution, but I can discuss, let's say, what would be the good idea to start designing the algorithms for the 2 questions you have, question 1 and question 2. Okay? All right, so if you don't have any question, then I will stop here. We'll post the video